Welcome to the Midnight Archives. Tonight we're going somewhere far from here. The lights are off, the room is quiet, and somewhere above the ceiling, above the atmosphere, above everything familiar, the universe is doing what it has always done. Expanding outward in every direction at once, carrying 2 trillion galaxies with it into a darkness without edges. The light reaching your eyes right now has already travelled for 8 minutes. It left the surface of the Sun at the speed of light, approximately 299,792 kilometers per second, and crossed the 150 million kilometers between the Sun and the Earth in the time it takes to boil an egg. That same light, if it were to continue past the Earth and keep travelling, would reach the Moon in just over a second. It would reach Mars, depending on where Mars happens to be in its orbit, somewhere between 3 and 22 minutes later. It would reach Jupiter in approximately 43 minutes. And by the time it reached the edge of the solar system, the boundary where the Sun's influence fades into the broader fabric of interstellar space, about 17 hours would have passed since it left the Sun's surface. The Sun itself is not a small thing. Its diameter is approximately 1.39 million kilometers, which means that roughly 1.3 million Earths could fit inside it if you were to pack them carefully together. Its mass accounts for approximately 99.86% of all the mass in the solar system. Everything else, the 8 planets, the dwarf planets, the moons, the asteroids, the comets, the dust and gas and ice that fills the space between them, makes up the remaining 0.14%. The Sun is not merely the dominant object in the solar system. It is, in almost every meaningful sense, the solar system, with the planets as afterthoughts orbiting in its outer regions. And yet the Sun is not particularly large as stars go. Among the hundreds of billions of stars in the Milky Way, the Sun sits comfortably in the middle range, what astronomers classify as a G-type main sequence star, sometimes called a yellow dwarf, though its light is closer to white than yellow when seen from space. There are stars in the galaxy that would dwarf the Sun in the way the Sun dwarfs the Earth. The star Uy-Scuti, located approximately 9,500 light-years from Earth in the constellation Scutum, has a radius approximately 1,700 times that of the Sun. If Uy-Scuti were placed at the centre of the solar system in the Sun's position, its surface would extend past the orbit of Jupiter. The Earth would be deep inside it, along with Mercury, Venus, Mars, the asteroid belt, and everything else that orbits within Jupiter's path. A light year is a distance, not a time. This is a distinction worth making clearly, because the word year in light year creates confusion. A light year is the distance that light travels in 1 year, approximately 9.46 trillion kilometers. The nearest star to the Sun, Proxima Centauri, is approximately 4.24 light-years away. This means that the light arriving from Proxima Centauri right now left that star 4.24 years ago. The star you're seeing when you look at Proxima Centauri, if you're somewhere dark enough to see it, which requires being in the southern hemisphere, is the star as it was more than 4 years in the past. You're not seeing the star as it is, you're seeing it as it was. This effect becomes more pronounced with distance. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is approximately 2.537 million light-years away. The light arriving from Andromeda tonight left that galaxy more than 2.5 million years ago, when the ancestors of modern humans were still making stone tools on the plains of Africa and had not yet spread beyond that continent. The galaxy you see when you look at Andromeda is not the galaxy that exists now. It is a record, a photograph, preserved in travelling light, of what Andromeda looked like in the distant past. The observable universe extends approximately 46 billion light-years in every direction from Earth. This might seem to contradict the age of the universe, which is approximately 13.8 billion years. If the universe is only 13.8 billion years old, how can we see objects 46 billion light-years away, since light travelling for 13.8 billion years could only have covered 13.8 billion light-years? The answer lies in the expansion of the universe. Space itself has been expanding since the Big Bang, carrying galaxies with it. Light that set out from distant regions 13.8 billion years ago has been travelling through space that was simultaneously expanding, so by the time it reaches us, the source of that light has moved much farther away than the distance the light itself has travelled. The universe is larger than its age in light years would suggest, because the universe has not been sitting still while the light travelled. Beyond the observable universe, the universe almost certainly continues. There is a horizon beyond which we cannot see, not because there is nothing there, but because light from those regions has not had time to reach us since the Big Bang. Whatever lies beyond that horizon is genuinely unknown. It may be more of the same, more galaxies, more stars, more space similar to what we can observe, or it may be radically different. Some cosmological models suggest that our observable universe is just one small region within a much larger whole, and that the conditions in other regions may be different in ways we cannot currently imagine. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in this estimate reflects the difficulty of counting stars in a galaxy you're inside. From Earth, we cannot step outside the Milky Way and look at it from a distance the way we can look at Andromeda. We are embedded in the disk of the galaxy, roughly 26,000 light-years from the galactic centre, and our view of the galaxy's structure is partially obscured by the gas and dust that fills the disk. Astronomers estimate the total number of stars by measuring the galaxy's mass and luminosity and comparing these to known properties of different types of stars, but the estimate carries considerable uncertainty. What is clear is that the number is enormous, hundreds of billions of individual suns, each with the potential to host its own family of planets. At the centre of the Milky Way, there is a supermassive black hole. It is called Sagittarius A star, pronounced Sagittarius A star, and it has a mass approximately 4 million times that of the Sun. Despite this enormous mass, Sagittarius A star is currently in a relatively quiet state. It is not actively consuming large amounts of material, and is not producing the powerful jets of energy that characterize the most active galactic nuclei. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, showing a bright ring of hot gas surrounding the dark shadow of the black hole's event horizon. The image confirmed what astronomers had long believed, that a supermassive black hole sits at the heart of our galaxy. A black hole's event horizon is not a physical surface, it is a boundary in space. The point of no return, the distance from the black hole's centre at which the escape velocity equals the speed of light. Nothing travelling at or below the speed of light can escape from within the event horizon, because the curvature of space-time within that boundary is so extreme that all paths, including the paths of light rays, curve inward toward the singularity at the black hole's centre. An object crossing the event horizon would not encounter any physical surface or barrier. It would simply cross an invisible line in space after which there was no way back. For a sufficiently large black hole, the tidal forces at the event horizon would be gentle enough that a person crossing it might not immediately notice anything unusual, though they would have no hope of returning to the universe outside. The first black hole ever directly imaged is called M87 star. Located at the centre of the galaxy Messier 87, approximately 55 million light-years from Earth, M87 star has a mass approximately 6.5 billion times that of the Sun. The image, released by the Event Horizon Telescope collaboration in 2019, shows a bright asymmetric ring of emission surrounding the dark shadow of the event horizon. The asymmetry in the ring, one side brighter than the other, is a consequence of the black hole's rotation. Material on the side of the ring moving toward us appears brighter, while material on the receding side appears dimmer. The image is a reconstruction from radio wave data collected simultaneously by 8 radio telescope facilities on different continents, producing an effective telescope the size of the Earth. Black holes come in a range of sizes that spans many orders of magnitude. Stellar mass black holes, formed by the gravitational collapse of massive stars at the end of their lives, typically have masses between a few and a few tens of times the mass of the Sun. A stellar mass black hole with 10 times the mass of the Sun would have an event horizon with a radius of approximately 30 kilometers. Supermassive black holes, found at the centers of most large galaxies, range from millions to billions of solar masses and have event horizons that can be larger than the solar system. Between these extremes, there is a class called intermediate mass black holes, with masses between about 100 and 100,000 solar masses whose existence has been suggested by various observations but is less firmly established. Neutron stars are among the densest objects in the known universe. They form when a massive star, typically one with a mass between 8 and 20 times that of the Sun, exhausts its nuclear fuel and its core collapses under gravity. The outer layers of the star are blown off in a supernova explosion. The core, if it does not have enough mass to collapse into a black hole, settles into a neutron star, an object typically between 1 and 2 solar masses, compressed into a sphere roughly 10 to 13 kilometers in diameter. The density is extraordinary. A teaspoon of neutron star material would weigh approximately 4 billion tons on Earth. The surface gravity of a neutron star is approximately 200 billion times that of Earth. Some neutron stars rotate hundreds of times per second. These rapidly rotating neutron stars are called millisecond pulsars. They emit beams of electromagnetic radiation from their magnetic poles, and as they rotate, these beams sweep across space like the beam of a lighthouse. When one of these beams happens to sweep across Earth, we detect a pulse of radio emission. The pulses arrive with extraordinary regularity. Millisecond pulsars keep time as accurately as some atomic clocks, making them useful as natural precision instruments for testing aspects of general relativity and searching for gravitational waves. The fastest known pulsar, PSRJ 1748-2 446 AD, rotates 716 times per second, meaning its surface is moving at approximately a quarter of the speed of light. A supernova explosion releases more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. When a massive star's core collapses and the outer layers bounce back in a supernova explosion, the energy released is staggering. Most of this energy, approximately 99%, is carried away not by the visible light, but by a flood of neutrinos produced in the collapsing core. The neutrino burst lasts only a few seconds, but its energy output is enormous. Supernovae are also the primary source of many of the heavy elements in the universe. Carbon, oxygen, silicon, iron, and most of the other elements heavier than hydrogen and helium were forged inside stars and scattered into space by supernova explosions, eventually forming new stars and planets and, in at least one case, living organisms. The gold in any jewellery you're wearing was forged in a neutron star merger. The very heaviest elements, gold, platinum, uranium, and others, cannot be produced efficiently in ordinary supernova explosions. Their creation requires the collision and merger of 2 neutron stars. When 2 neutron stars spiral together and collide, the event releases gravitational waves and produces an explosion called a kilonova, which generates heavy elements through a process called rapid neutron capture. In 2017, the gravitational wave event GW 170817 was observed to be accompanied by a kilonova, and the spectrum of light from that kilonova showed clear signatures of gold and other heavy elements being produced. The atoms of gold in any ring or necklace were created in an event like this, a neutron star merger that occurred somewhere in the galaxy billions of years ago, scattering the newly forged gold into the interstellar medium, where it eventually became part of the cloud of gas and dust from which the solar system formed. The solar system formed approximately 4.6 billion years ago from a cloud of gas and dust. The process began when a region of a molecular cloud began to collapse under its own gravity. As it collapsed, it spun faster and flattened into a rotating disk. The center grew hotter and denser, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. The Sun was born. In the disk surrounding the young Sun, particles stuck together, growing from microscopic grains to pebbles to rocks to planetesimals to the planets we know today. The entire process, from the initial collapse to the formation of the terrestrial planets, took roughly 100 million years. Jupiter is so massive that it technically does not orbit the Sun. All planets orbit the common centre of mass of the planet-Sun system, called the barycenter. For most planets, this barycenter lies so close to the centre of the Sun that the distinction is negligible. But Jupiter is massive enough, approximately 318 times the mass of the Earth, and 2.5 times the mass of all the other planets combined, that the barycenter of the Jupiter-Sun system lies just outside the surface of the Sun. Technically, both Jupiter and the Sun orbit this point. Jupiter's gravitational influence extends throughout the solar system and is responsible for the Kirkwood gaps in the asteroid belt, regions where orbits are destabilized by resonances with Jupiter's orbital period. Saturn's rings are far younger than Saturn itself. Saturn formed approximately 4.5 billion years ago, at roughly the same time as the rest of the solar system. But measurements from the Cassini spacecraft suggested that the rings are far younger, perhaps only 10 to 100 million years old. The rings consist mostly of ice and rock spread across a disk, that extends up to 282,000 kilometers from Saturn's center, but is only a few tens of meters thick in most places. The leading hypothesis for their origin is that they formed from the destruction of a moon or comet torn apart by tidal forces. The rings are also slowly disappearing, material is continuously raining down into Saturn's atmosphere, and at current rates the rings will be gone in another 100 million years or so. The surface of Venus is hotter than the surface of Mercury, despite being nearly twice as far from the Sun. Mercury has almost no atmosphere and cannot retain heat. Its surface temperature swings between approximately 430 degrees Celsius on the sunlit side and minus 180 degrees Celsius on the night side. Venus, by contrast, has an extremely dense atmosphere of carbon dioxide that creates a runaway greenhouse effect so extreme that the average surface temperature is approximately 465 degrees Celsius, hot enough to melt lead, with almost no variation between day and night. The atmospheric pressure on the surface of Venus is approximately 90 times that at sea level on Earth, equivalent to the pressure found about 900 meters beneath the ocean surface. Mars has the largest volcano in the solar system. Olympus Mons rises approximately 21.9 kilometers above the Martian surface and has a base diameter of approximately 600 kilometers, roughly the size of the state of Arizona. It can be so large partly because Mars has no tectonic plates. On Earth, volcanoes are carried away from their magma sources as tectonic plates move. On Mars, the crust does not move, so the same volcanic hotspot has been depositing material in the same location for billions of years. Mars also hosts the largest canyon in the solar system. Valles Marineris stretches approximately 4,000 kilometers along the Martian equator, roughly the width of the continental United States, and reaches depths of up to 7 kilometers. The Grand Canyon in Arizona, by comparison, is approximately 446 kilometers long and about 1.6 kilometers deep. Valles Marineris formed primarily through tectonic rifting billions of years ago, its walls pulled apart by geological forces rather than carved by any river. Water ice exists in permanently shadowed craters at the poles of the Moon. At the lunar poles, there are craters whose floors are in permanent shadow, never receiving direct sunlight. In these permanently shadowed regions, temperatures can fall to approximately minus 240 degrees Celsius, among the coldest surfaces in the solar system. Water ice delivered by comets and asteroids over billions of years has been preserved in these cold traps, never warming enough to evaporate. This ice, confirmed by multiple spacecraft, represents a potential resource for future human exploration. The Moon is slowly moving away from the Earth. Each year, the Moon recedes from the Earth by approximately 3.8 centimeters. This recession is a consequence of tidal interactions. The Moon's gravity raises tidal bulges in the Earth's oceans and crust, and because the Earth rotates faster than the Moon orbits, these bulges are carried slightly ahead of the Earth-Moon line. The gravitational attraction of these bulges pulls on the Moon, adding energy to its orbit and causing it to move to a higher, more distant orbit. Billions of years ago, when the Moon was much closer, days on Earth were much shorter, perhaps only 6 hours long. The universe is approximately 13.8 billion years old. This age has been determined through multiple independent methods, including measurements of the cosmic microwave background, the faint glow of radiation left over from the early universe, released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely through space for the first time. The pattern of tiny temperature fluctuations in this radiation carries detailed information about the geometry, composition, and age of the universe. In the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion called inflation. During inflation, the universe expanded by a factor of at least 10 to the power of 26 in an interval of time so brief it makes any ordinary measure of brevity seem leisurely. This rapid expansion smoothed out any initial irregularities in the distribution of matter and energy, explaining why the cosmic microwave background looks almost perfectly uniform in every direction. Tiny quantum fluctuations stretched to macroscopic scales became the seeds of all the large-scale structure in the universe, the first density variations that eventually collapsed under gravity to form the first stars and galaxies. The universe is expanding, and its expansion is accelerating. In 1929, Edwin Hubble published observations showing that distant galaxies are receding from us, and that the more distant a galaxy is, the faster it is receding. This recession is not the motion of galaxies through space, but the expansion of space itself carrying galaxies with it. In 1998, two independent teams of astronomers studying distant supernovae discovered that the expansion of the universe is not slowing down, as gravity would be expected to cause, but accelerating. This acceleration is attributed to dark energy, which appears to act as a repulsive force permeating all of space, and accounts for approximately 68% of the total energy content of the universe. Dark matter accounts for approximately 27% of the universe's total energy content. It does not emit, absorb, or reflect light, making it invisible to telescopes. Its existence is inferred from its gravitational effects, the way it influences the motions of stars within galaxies, the behavior of galaxy clusters, and the bending of light through gravitational lensing. Without dark matter, the outer stars of spiral galaxies would orbit too slowly to match observations. The nature of dark matter remains one of the deepest unsolved problems in physics. It is not made of ordinary atoms, does not interact with light, and decades of sensitive experiments searching for dark matter particles have so far produced no definitive detection. The remaining approximately 5% of the universe's energy content is ordinary matter, atoms, the stuff that makes up stars, planets, and everything we can directly see and touch. This fraction, 5%, is all the matter that has ever been observed directly in the history of science. Everything that astronomers have ever looked at through telescopes, everything that physicists have ever studied in laboratories, everything that living organisms are made of, constitutes a small minority of the universe's total content. The majority of the universe is made of things whose nature we do not understand. The majority of the universe is made of things whose nature we do not understand. And yet, from the small fraction of the universe that we can observe, that 5% of ordinary matter distributed across billions of galaxies, we have learned an extraordinary amount. We have mapped the cosmic web. We have measured the age of the universe to within a few tens of millions of years. We have traced the history of stars and galaxies back to within a few 100 million years of the Big Bang. We have detected gravitational waves from colliding black holes a billion light-years away. We have imaged the shadow of a black hole's event horizon. And we have done all of this from a single pale blue planet, orbiting an unremarkable star in the outer disk of one ordinary galaxy among hundreds of billions. The cosmic web is the largest structure in the observable universe. On the very largest scales, matter in the universe is not distributed uniformly, but is organized into a vast three-dimensional network of filaments, sheets, and walls of galaxies separated by enormous voids nearly empty of matter. This structure, called the cosmic web, was seeded by the tiny density fluctuations of the early universe and grew over the subsequent 13 billion years under the gravitational influence of dark matter. The filaments of the cosmic web are typically tens to hundreds of millions of light-years long. The voids between them can span hundreds of millions of light-years across. Galaxy clusters, the largest gravitationally bound structures in the observable universe, sit at the intersections of these filaments, where multiple strands of the web converge and concentrate. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall. Discovered in 2013 and confirmed through subsequent observations, this enormous structure spans approximately 10 billion light-years, roughly a tenth of the diameter of the observable universe. It consists of a massive concentration of galaxies extending across a region of space so vast that light takes 10 billion years to cross it. The existence of structures this large poses something of a challenge to standard cosmological models, which predict that matter should not be able to cluster on scales much larger than a few 100 million light-years in a universe as old as ours. The Hercules Corona Borealis Great Wall is large enough that some cosmologists have questioned whether it constitutes a single, coherent structure, or is instead a statistical artifact of the way galaxy surveys are conducted. The debate continues. The observable universe contains approximately 2 trillion galaxies. This estimate, published in 2016 by a team led by astronomer Christopher Consolis, was derived by combining deep field images from the Hubble Space Telescope with mathematical models to account for galaxies too faint or too distant to be directly observed. The number, 2 trillion, is roughly 10 times larger than previous estimates, which had placed the number of galaxies in the observable universe at around 200 billion. Most of these additional galaxies are small, faint dwarf galaxies in the distant universe, detectable only through statistical inference rather than direct observation. The total number of stars in the observable universe is therefore also much larger than previously estimated, a number so large that expressing it in ordinary language becomes essentially meaningless. Galaxies come in three broad shapes: elliptical, spiral, and irregular. Elliptical galaxies are roughly spherical or elongated ellipsoids of stars, containing mostly older red and yellow stars and very little gas or dust. They are the largest galaxies in the universe by mass, and some giant elliptical galaxies contain trillions of stars. Spiral galaxies like the Milky Way and Andromeda have a central bulge surrounded by a flattened disk in which spiral arms of younger, brighter stars and gas trace out curving structures. Irregular galaxies have no regular shape and are often the product of gravitational interactions or mergers between other galaxies. The relative abundance of these types changes with distance, and therefore with cosmic time. The early universe contained more irregular and compact galaxies, while the familiar spiral and elliptical shapes became more common as the universe aged. The Milky Way and Andromeda are on a collision course. In approximately 4.5 billion years, the Andromeda Galaxy and the Milky Way will begin to collide and merge. This collision, confirmed by Hubble Space Telescope measurements of Andromeda's proper motion across the sky, will unfold over several billion years and will not be a violent event in the way that word suggests. The stars in each galaxy are so far apart relative to their size that direct stellar collisions will be extremely rare. The chances of any two specific stars colliding during the merger are extraordinarily small. Instead, the two galaxies will pass through each other, their shapes distorting dramatically under the influence of gravitational tidal forces, stars being flung into new orbits, gas clouds colliding and triggering bursts of new star formation. Eventually, after multiple passages, the two galaxies will settle into a single merged system, a large elliptical galaxy sometimes called Milkomeda, over a timescale of several billion years. The Sun, if it still exists by then, will likely find itself in a very different part of the merged galaxy than it currently occupies. The Sun will eventually become a red giant and then a white dwarf. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core that currently powers nuclear fusion. As the core contracts under gravity and heats up, the outer layers of the Sun will expand enormously, and the Sun will swell into a red giant star. At its maximum extent, the Sun's radius may reach somewhere between 100 and 200 times its current size. Mercury and Venus will certainly be engulfed. Whether the expanding Sun will reach the Earth's current orbit is uncertain. The loss of mass from the Sun will cause the Earth's orbit to expand outward as the Sun grows, and it is possible the Earth may just barely survive the red giant phase, though its oceans will have boiled away, and its surface will have been rendered utterly uninhabitable long before the Sun reaches its maximum size. Eventually, the outer layers of the red giant will be expelled, forming a glowing shell of gas called a planetary nebula that will expand into space over tens of thousands of years. The remaining core, roughly half the Sun's current mass, compressed into a sphere roughly the size of the Earth, will be a white dwarf, a dense, hot object that slowly cools over billions of years with no nuclear fuel to sustain it. White dwarfs can persist for trillions of years. A white dwarf shines not through nuclear fusion, but by radiating away the heat stored in its dense interior. This process is extraordinarily slow. The current age of the universe, 13.8 billion years, is far shorter than the time required for a white dwarf to cool significantly. The oldest white dwarfs currently observable are still warm enough to glow faintly with a bluish-white light. Over many billions of years, a white dwarf will cool through white to yellow to orange to red, and eventually, in principle, to a cold dark object called a black dwarf, the theoretical endpoint of white dwarf evolution. However, the time required for a white dwarf to cool completely to a black dwarf is estimated to be far longer than the current age of the universe. No black dwarfs are thought to exist yet anywhere in the observable universe. Some stars end their lives in explosions so powerful they briefly outshine entire galaxies. A Type 1. A supernova occurs in a binary star system where one star is a white dwarf and the other is a companion star, often a red giant. The white dwarf gradually accretes material from its companion, and when it accumulates enough mass to approach a critical threshold, approximately 1.4 times the mass of the Sun, a limit called the Chandrasekhar limit. Carbon fusion ignites throughout the white dwarf nearly simultaneously. The resulting thermonuclear explosion completely destroys the white dwarf in seconds, releasing energy equivalent to roughly a billion megatons of TNT. Because all Type 1a supernovae occur at approximately the same mass, and therefore release approximately the same energy, they have almost the same intrinsic brightness, making them useful as standard candles for measuring cosmic distances. It was by observing Type 1a supernovae in distant galaxies that astronomers in 1998 discovered that the expansion of the universe is accelerating. Gamma-ray bursts are the most energetic explosions in the observable universe. They are brief, intense flashes of gamma radiation that appear from random directions in the sky, typically lasting from a fraction of a second to a few minutes, and releasing more energy in that brief interval than the Sun will emit over its entire lifetime. They are detected by space-based telescopes at a rate of roughly one per day, though each one is visible only once and from only one direction. Gamma-ray bursts come in two varieties. Short gamma-ray bursts, lasting less than about 2 seconds, are now believed to be produced by the merger of two neutron stars, or a neutron star and a black hole, the same type of event that produces gravitational waves and colonovae. Long gamma-ray bursts, lasting more than 2 seconds, are associated with the core collapse of massive rapidly rotating stars into black holes. The afterglow of a gamma-ray burst, the fading emission at longer wavelengths that persists after the initial burst, has been detected at distances corresponding to a time when the universe was only a few 100 million years old, making gamma-ray bursts among the most distant and energetic phenomena ever observed. The International Space Station orbits the Earth at an altitude of approximately 400 kilometers. At that altitude, the station is traveling at approximately 7.66 kilometers per second, which means it completes one orbit of the Earth every 92 minutes. The crew of the station therefore sees approximately 16 sunrises and sunsets every 24 hours. At its orbital altitude, the ISS is still within the Earth's tenuous upper atmosphere, the exosphere, and experiences a small but measurable atmospheric drag that gradually lowers its orbit. Periodic reboosts using the engines of docked spacecraft are required to maintain the station's altitude. The station has been continuously inhabited by rotating crews of astronauts and cosmonauts since November 2000, making it the longest continuously inhabited human structure in the history of spaceflight. The Voyager 1 spacecraft is the most distant human-made object ever created. Launched on September 5, 1977, Voyager 1 is now more than 23 billion kilometers from the Sun, far beyond the orbit of Neptune and well into interstellar space. It crossed the heliopause, the boundary where the solar wind is stopped by the interstellar medium, in 2012, becoming the first human-made object to enter interstellar space. Despite being more than 46 years into its journey, Voyager 1 continues to transmit data back to Earth, though the radio signal takes more than 22 hours to travel the distance between the spacecraft and Earth at the speed of light. The spacecraft carries a golden record containing sounds and images intended to communicate the nature of life and civilization on Earth to any extraterrestrial intelligence that might someday encounter it. A gesture that is, in its way, both scientifically futile and profoundly human. Light from the Voyager, one spacecraft takes more than 22 hours to reach Earth. The signal from Voyager 1 travelling at the speed of light takes this long to cover the distance between the spacecraft and Earth. By comparison, the nearest star beyond the Sun, Proxima Centauri, at 4.24 light-years, is approximately 1,600 times farther away than Voyager 1's current position. Even travelling at Voyager 1's current speed of approximately 17 kilometers per second, it would take the spacecraft approximately 73,000 years to reach Proxima Centauri, if it were heading in that direction, which it is not. The distances between stars are so vast that even our fastest spacecraft, travelling at speeds that seem extraordinary by terrestrial standards, would require timescales far longer than recorded human history to traverse them. The nearest potentially habitable exoplanet may be orbiting the star closest to the Sun. Proxima Centauri b, discovered in 2016, is a planet orbiting Proxima Centauri, the closest star to the Sun at 4.24 light-years away, within the habitable zone where liquid water could potentially exist on its surface. The planet has a minimum mass approximately 1.07 times that of the Earth. However, whether it is actually habitable is uncertain. Proxima Centauri is a red dwarf star that emits powerful flares of ultraviolet and X-ray radiation that may strip away any atmosphere the planet might have. The planet also orbits so close to its star, much closer than Mercury orbits the Sun, that it is likely tidally locked, with one hemisphere in permanent daylight and the other in permanent darkness. Whether habitable conditions could exist on a tidally locked planet is an open question in planetary science. More than 5,000 exoplanets have been confirmed as of the early 2000s. An exoplanet is a planet orbiting a star other than the Sun. The first confirmed exoplanets were detected in the early 1990s. The discovery rate accelerated dramatically following the launch of the Kepler Space Telescope in 2009, which monitored the brightness of approximately 150,000 stars continuously for 4 years, looking for the tiny dips in brightness caused when a planet passes in front of its host star. Kepler discovered thousands of exoplanet candidates, the majority of which have been confirmed through follow-up observations. The discoveries have revealed a remarkable diversity of planetary systems very different from our own solar system, with multiple planets packed close to their host stars, or giant planets orbiting much closer than Mercury orbits the Sun, or planets in wildly eccentric orbits. The solar system, it turns out, is not a typical planetary system. Some exoplanets are unlike anything in our solar system. Hot Jupiters are gas giant planets orbiting extremely close to their host stars, completing one orbit in just a few days and reaching surface temperatures of thousands of degrees Celsius. They were the first exoplanets detected around Sun-like stars, not because they are the most common type of planet, but because their large size and short orbital periods made them the easiest to detect with early techniques. Super-Earths are planets with masses between 1 and 10 times that of the Earth, larger than any rocky planet in the solar system but smaller than Neptune. They are actually the most common type of planet known in the galaxy. Mini-Neptunes are intermediate between super-Earths and Neptune-sized planets, with thick gaseous envelopes. The prevalence of these planet types in the galaxy suggests that planetary systems can take forms very different from the neat progression of small rocky planets followed by large gas giants that characterizes our own solar system. The James Webb Space Telescope can detect the atmospheres of exoplanets. Launched on December 25, 2021, the James Webb Space Telescope is the largest and most powerful space telescope ever deployed. Its 6.5-meter primary mirror, far larger than Hubble's 2.4-meter mirror, and its location approximately 1.5 million kilometers from Earth at the second Lagrange point, give it extraordinary sensitivity to infrared radiation. When a planet passes in front of its host star, some of the starlight filters through the planet's atmosphere, and the specific wavelengths absorbed by that atmosphere leave signatures in the spectrum of light that reach the telescope. By comparing the spectrum of the star alone with the spectrum of the star plus planet, astronomers can infer the chemical composition of the planet's atmosphere. Webb has already detected carbon dioxide, methane, water vapor, and sulfur dioxide in the atmospheres of several exoplanets, demonstrating the feasibility of atmospheric characterization for worlds beyond our solar system. Europa, a moon of Jupiter, is one of the most promising places in the solar system to search for life. Europa is roughly the size of the Earth's moon, but beneath its icy surface it harbours a global ocean of liquid water, kept liquid by the tidal heating caused by Jupiter's powerful gravity continuously flexing the moon's interior. The ocean is estimated to be between 60 and 150 kilometers deep, containing more liquid water than all of Earth's oceans combined. At the bottom of this ocean, where the water meets the rocky seafloor, conditions may be similar to those at Earth's hydrothermal vents, environments that on Earth support rich ecosystems of organisms that derive energy from chemical reactions rather than sunlight. The Galileo spacecraft detected magnetic field signatures consistent with a subsurface conducting layer, almost certainly saltwater, when it flew past Europa in the 1990s. NASA's Europa Clipper mission, launched in 2024, is designed to make detailed observations of Europa's surface and subsurface to assess its habitability and look for signs of activity in its ocean. Enceladus, a moon of Saturn, actively vents water from its subsurface ocean into space. Enceladus is a small moon, only about 504 kilometers in diameter, but it is one of the most geologically active bodies in the solar system. Near its south pole, a series of long parallel fractures in the ice, nicknamed the Tiger Stripes, vent plumes of water vapor, ice particles, and organic molecules into space. These plumes feed Saturn's E-ring and were discovered by the Cassini spacecraft in 2005. The material in the plumes has been analysed in detail by Cassini, revealing the presence of water, carbon dioxide, methane, molecular hydrogen, and complex organic compounds. The presence of molecular hydrogen is particularly significant. On Earth, the reaction between hydrogen-rich water and iron-containing rocks at hydrothermal vents produces molecular hydrogen, and this reaction supports chemosynthetic ecosystems. The detection of molecular hydrogen in Enceladus's plumes suggests that similar hydrothermal activity may be occurring in its subsurface ocean. Enceladus has become one of the highest priority targets in the search for extraterrestrial life. Titan, Saturn's largest moon, has lakes and rivers of liquid methane. Titan is the only moon in the solar system with a dense atmosphere. Its surface pressure is about 1.5 times that of Earth at sea level, and the only world other than Earth known to have stable bodies of liquid on its surface. But the liquid is not water. At Titan's surface temperature of approximately -179 degrees Celsius, water is a rock-hard solid. Instead, the lakes and rivers and seas of Titan are filled with liquid methane and ethane. The Huygens probe, which landed on Titan in 2005 after being released by the Cassini spacecraft, returned images of rounded pebbles that appeared to have been shaped by the flow of liquid, similar to river rocks on Earth. Radar observations from Cassini revealed large lakes and seas near the North Pole, including Kraken Mare, which is larger than the Caspian Sea. Whether any form of life could exist in Titan's methane lakes, using liquid methane as a solvent in the way that Earth life uses water, is a question that cannot currently be answered, but has been seriously considered by astrobiologists. Mars once had a global magnetic field that protected it from solar wind. Today, Mars has no global magnetic field, only scattered patches of magnetism in its ancient crust, relics of a time when the planet had an active magnetic dynamo in its core. Between approximately 4 billion and 3.7 billion years ago, Mars had a magnetic field comparable in strength to Earth's, which would have shielded its atmosphere from the stripping effects of the solar wind. When the dynamo stopped, the reason is not entirely clear, but it may be related to the cooling and solidification of the Martian core. The solar wind began to erode the Martian atmosphere. Over billions of years, the pressure dropped from levels that may have been comparable to Earth's, to the current pressure of less than 1% of Earth's atmospheric pressure at sea level. The loss of the magnetic field may have been one of the primary reasons Mars transitioned from a warmer, wetter world to the cold, dry desert it is today. The surface of Mars experiences planet-wide dust storms that can last for months. Mars has a very thin atmosphere, but the dust particles on its surface are light and fine enough that strong winds can loft them high into the atmosphere. Occasionally, local dust storms grow into regional storms, and sometimes regional storms expand until they cover the entire planet. During a global dust storm, the sun is obscured and temperatures on the surface can drop significantly. The Opportunity rover, which landed on Mars in 2004 and operated for nearly 15 years, finally lost contact with Earth in June 2018 when a global dust storm blocked the sunlight that powered its solar panels. Global dust storms on Mars occur roughly every 2 to 3 Martian years, which is approximately every 4 to 6 Earth years, though their exact timing and intensity are difficult to predict. The asteroid belt between Mars and Jupiter contains millions of objects but is mostly empty space. Science fiction has popularized the image of the asteroid belt as a dense, dangerous field of rocks through which spacecraft must navigate carefully. In reality, the asteroid belt is mostly empty. The total mass of all the asteroids in the belt is approximately 4% of the mass of the Moon. The average distance between asteroids is roughly 1 million kilometers, which is why spacecraft traveling through the asteroid belt, including the Pioneer, Voyager, New Horizons and many others, have done so without incident. The largest object in the asteroid belt is the dwarf planet Ceres, which accounts for approximately 1/3 of the belt's total mass. Ceres was discovered in 1801, and for several decades was considered a planet before the discovery of many similar objects led to its reclassification. The Dawn spacecraft orbited Ceres from 2015 to 2018, and discovered bright spots on its surface that turned out to be deposits of salt left behind by water that had evaporated from its interior. Pluto was discovered in 1930 and reclassified as a dwarf planet in 2006. Pluto's discovery was the result of a deliberate search for a hypothetical Planet X, a large planet thought to be perturbing the orbits of Uranus and Neptune. The search was organised by Percival Lowell and continued after his death at the Lowell Observatory in Flagstaff, Arizona. The young astronomer Clyde Tombaugh discovered Pluto in February 1930 by comparing photographic plates taken on different nights and noticing a faint point of light that had moved. Pluto was hailed as the 9th planet and remained so for 76 years. In 2006, the International Astronomical Union adopted a formal definition of planet that required an object to have cleared the neighbourhood of its orbit. Pluto, sharing its orbital neighbourhood with many other Kuiper Belt objects, did not meet this criterion and was reclassified as a dwarf planet, a decision that remains controversial among some astronomers and much of the general public. The New Horizons spacecraft revealed Pluto to be a geologically active world. Before New Horizons flew past Pluto in July 2015, the first spacecraft to visit the outer solar system beyond Neptune, most astronomers expected Pluto to be a cold, geologically dead ball of ice and rock. What they found instead was a world of stunning complexity. Vast plains of nitrogen ice, mountains of water ice reaching heights of over 3,000 meters, a thin but detectable atmosphere, possible evidence of past geological activity or cryovolcanism, and a heart-shaped region of smooth nitrogen ice covering an area roughly the size of Texas that has been named Tombaugh Regio, in honor of Pluto's discoverer. The smooth plains of Tombaugh Regio show very few impact craters, suggesting they are geologically young, perhaps only tens of millions of years old in a body that formed 4.6 billion years ago. The mechanism sustaining this geological activity in a world so far from the Sun and so small that it was expected to be cold and inert is not fully understood. The Oort cloud is a vast spherical shell of icy bodies surrounding the solar system. At distances ranging from roughly 2,000 to 100, 0 astronomical units from the Sun, where 1 astronomical unit is the average Earth-Sun distance of 150 million kilometers, there is thought to exist a vast reservoir of icy bodies left over from the formation of the solar system. This structure, called the Oort cloud after the Dutch astronomer Jan Oort, who first proposed its existence in 1950, is thought to contain trillions of icy objects, though it has never been directly observed. The outer edge of the Oort cloud is so far from the Sun that it extends nearly a quarter of the way to Proxima Centauri. Long-period comets, comets with orbital periods of thousands to millions of years, are thought to originate in the Oort cloud, dislodged from their distant orbits by gravitational perturbations from passing stars or the galactic tide, and sent on long, swooping trajectories into the inner solar system. Comets are made of ice and rock, and have been delivering organic molecules to the inner solar system for billions of years. A comet is essentially a dirty snowball, a nucleus of ice, rock, and organic compounds typically a few kilometers to tens of kilometers across, preserved in the cold outer solar system since the formation of the solar system 4.6 billion years ago. When a comet falls into the inner solar system and approaches the Sun, the surface ice sublimates, converts directly from solid to gas, producing a coma, a diffuse cloud of gas and dust surrounding the nucleus that can be hundreds of thousands of kilometers across. The solar wind and radiation pressure push this material away from the Sun, creating the comet's characteristic tails, a blue-white ion tail pointing directly away from the Sun, and a yellowish dust tail curving along the comet's orbital path. Comets may have played a role in delivering water and organic molecules to the early Earth, contributing to the conditions that eventually gave rise to life. The Rosetta spacecraft, which orbited the comet 67P/Churyumov-Gerasimenko from 2014 to 2016, detected complex organic molecules including glycine, the simplest amino acid, in the comet's coma. General relativity predicts that massive objects curve the fabric of space-time. Einstein's general theory of relativity, published in 1915, describes gravity not as a force between masses, as Newton had described it, but as the curvature of space-time caused by the presence of mass and energy. Objects moving through curved space-time follow the straightest possible paths, called geodesics, and these curved paths are what we observe as the effects of gravity. A planet orbits the Sun not because the Sun pulls it with a gravitational force, but because the Sun's mass curves the space-time around it, and the planet is following the straightest path available in that curved geometry. General relativity makes predictions that differ from Newton's theory of gravity in several ways, and all of these predictions have been confirmed by experiment. The perihelion precession of Mercury's orbit, the slow rotation of the point of Mercury's closest approach to the Sun, was explained precisely by general relativity but could not be explained by Newtonian gravity. The bending of starlight around the Sun, first measured during the solar eclipse of 1919, was predicted by general relativity and confirmed by observation. The existence of gravitational waves, ripples in the fabric of spacetime produced by accelerating masses, was predicted by Einstein in 1916 and confirmed by the first detection in 2015. Gravitational waves travel at the speed of light and were first directly detected in 2015. On September 14, 2015, the LIGO gravitational wave detectors in Hanford, Washington and Livingston, Louisiana detected a gravitational wave signal lasting approximately 0.2 seconds. The signal was produced by the merger of two black holes, one with a mass approximately 29 times that of the Sun, the other approximately 36 times that of the Sun, that occurred approximately 1.3 billion light-years from Earth. As the two black holes spiraled together and merged, they converted approximately 3 solar masses of material directly into gravitational wave energy in a fraction of a second, briefly releasing more power than all the stars in the observable universe combined. The gravitational wave signal swept through the Earth, stretching and squeezing the planet by a tiny fraction of the diameter of a proton as it passed. The LIGO detectors, which measure changes in the length of 4-kilometer arms using laser interferometry, detected this minuscule distortion with extraordinary precision. The discovery, announced in February 2016, confirmed a major prediction of general relativity and opened a new era in astronomy. Time runs slower in stronger gravitational fields. This effect, called gravitational time dilation, is a direct consequence of general relativity. A clock at lower altitude, closer to a massive body, runs slower than an identical clock at higher altitude. The difference is tiny under ordinary circumstances. A clock at sea level runs slower than a clock on a mountaintop by only about a few microseconds per year. But in more extreme gravitational environments, the effect becomes more pronounced. Near the event horizon of a black hole, time dilation becomes extreme. A clock hovering just outside the event horizon would appear, to a distant observer, to run nearly infinitely slowly. For the infalling object itself, nothing unusual would be observed locally, but the universe outside would appear to evolve at an accelerated rate. GPS satellites, which orbit at an altitude of approximately 200 kilometers, experience weaker gravity than clocks on Earth's surface, and therefore run faster by about 45 microseconds per day due to gravitational time dilation. If this effect were not corrected for, GPS accuracy would degrade by approximately 10 kilometers per day. Time also runs slower for objects moving at high velocities. This effect, called special relativistic time dilation, arises from Einstein's special theory of relativity, published in 1905. According to special relativity, the laws of physics are the same in all inertial frames of reference, and the speed of light is constant for all observers regardless of their motion. A consequence of these postulates is that time passes more slowly for objects moving at high velocities relative to a stationary observer. This is not a perceptual illusion. It is a real difference in the rate at which time passes for differently moving objects. For everyday velocities, the effect is negligible, but at velocities approaching the speed of light, the effect becomes significant. A hypothetical astronaut travelling to Proxima Centauri at 99.5% of the speed of light would age approximately 4.3 years during the journey, but on Earth, approximately 43 years would pass. When the astronaut returned, if they returned at the same speed, they would be about 8.6 years older, while Earth would have aged more than 86 years. This is the twin paradox, and while it sounds paradoxical, it is a genuine and experimentally confirmed prediction of special relativity. The speed of light in a vacuum is approximately 299,792 kilometers per second, and nothing with mass can reach it. This is one of the most fundamental facts in physics. According to special relativity, as an object with mass is accelerated, it gains energy, and its effective mass increases. As its speed approaches the speed of light, the energy required to accelerate it further approaches infinity. An infinite amount of energy would be required to accelerate any object with mass to exactly the speed of light, which is why it is impossible. The speed of light is therefore not merely a very fast speed that we happen not to be able to reach with current technology. It is a fundamental upper limit built into the structure of space-time. Massless particles such as photons and gravitons travel at exactly the speed of light. Particles with mass can approach it arbitrarily closely with sufficient energy, but can never reach or exceed it. Stars spend most of their lives fusing hydrogen into helium. This process, called hydrogen burning in stellar physics, occurs in the cores of main sequence stars, the broad middle range of the stellar life cycle that the Sun is currently in. In the Sun's core, approximately 600 million tons of hydrogen are converted into helium every second. This conversion releases energy through the famous equation E equals mc squared. A small amount of mass is converted into a large amount of energy. The Sun has been doing this for approximately 4.6 billion years and has enough hydrogen remaining in its core to continue for approximately another 5 billion years. The energy produced in the Sun's core takes tens of thousands to millions of years to diffuse outward to the surface, bouncing between particles in the dense interior in a random walk. Once it reaches the surface, it escapes as sunlight and makes the 8-minute journey to Earth. The core of the Sun reaches a temperature of approximately 15 million degrees Celsius. At this temperature, hydrogen nuclei, protons, move fast enough that quantum tunneling allows them to fuse together despite the electromagnetic repulsion between their positive charges. The fusion process in the Sun proceeds through a series of steps called the proton-proton chain, which converts 4 protons into 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and energy. Each step in the chain occurs at a different rate, and the slowest step, the initial fusion of 2 protons to form a deuterium nucleus, limits the overall rate. This slow rate is actually fortunate for life on Earth. If the proton-proton chain proceeded more quickly, the Sun would have burned through its hydrogen fuel long before complex life had time to evolve. Approximately 2% of the Sun's energy escapes as neutrinos. Solar neutrinos were first detected on Earth in the 1960s by physicist Raymond Davis Jr., who built a detector consisting of 100,000 gallons of cleaning fluid deep in the Homestake gold mine in South Dakota. The detector was designed to capture the tiny fraction of neutrinos passing through it. Despite the enormous number of solar neutrinos streaming through the Earth at any moment, their interaction with matter is so weak that most pass straight through the Earth without interacting at all. Davis detected far fewer neutrinos than theory predicted, leading to the solar neutrino problem, a discrepancy that persisted for decades. The solution, confirmed in the early 2000s, was that neutrinos oscillate between 3 different types, or flavors, as they travel, and Davis's detector was only sensitive to one flavor. The discovery of neutrino oscillations implied that neutrinos have a small but non-zero mass, which was not initially predicted by the standard model of particle physics. The Sun's surface, called the photosphere, has a temperature of approximately 5,500 degrees Celsius. Above the photosphere, the Sun's atmosphere thins into the chromosphere and then the corona. The corona, the Sun's outer atmosphere, visible as the white halo surrounding the Sun during a total solar eclipse, has a temperature of approximately 1 to 3 million degrees Celsius. This is far hotter than the photosphere below it, and the reason for this temperature inversion, why the outer atmosphere should be so much hotter than the surface, has puzzled solar physicists for decades. The leading hypothesis is that the corona is heated by the dissipation of magneto-hydrodynamic waves propagating along magnetic field lines from the solar interior, but the details of this process are still not fully understood. The Parker Solar Probe, launched in 2018 and designed to fly closer to the Sun than any previous spacecraft, is currently collecting data that may help resolve this mystery. Solar flares and coronal mass ejections can disrupt technology on Earth. A solar flare is a sudden, intense burst of radiation from the Sun's surface, caused by the rapid release of magnetic energy. A coronal mass ejection is a large cloud of magnetized plasma expelled from the Sun's corona into interplanetary space. When a powerful coronal mass ejection is directed toward Earth, it can interact with Earth's magnetic field and cause a geomagnetic storm. Geomagnetic storms can induce electric currents in long conductors such as power lines and pipelines, potentially damaging electrical infrastructure. They can also disrupt radio communications and GPS signals and damage satellites in orbit. The largest geomagnetic storm in recorded history, the Carrington event of 1859, was powerful enough to set telegraph systems on fire in North America and Europe. A similar event today would cause far more damage given the extent of modern electrical and electronic infrastructure. The economic cost of a repeat Carrington event has been estimated in the trillions of dollars. Auroras are produced when charged particles from the Sun collide with atoms in Earth's upper atmosphere. Electrons and protons from the solar wind, channeled by Earth's magnetic field toward the polar regions, collide with oxygen and nitrogen atoms in the upper atmosphere at altitudes of roughly 100 to 300 kilometers. These collisions excite the atoms to higher energy states, and when the atoms return to their ground states, they emit light. Oxygen atoms produce the most common colors of aurora: green at lower altitudes, around 100 to 150 kilometers, and red at higher altitudes above 200 kilometers. Nitrogen produces blue and violet hues. The result is the shimmering dynamic curtains of light, the northern and southern lights, that appear at high latitudes during periods of elevated solar activity. Auroras can extend to lower latitudes during major geomagnetic storms. The Carrington event produced auroras visible in the tropics. Earth's magnetic field is generated by the motion of liquid iron in its outer core. The Earth's interior consists of a solid inner core of iron and nickel, approximately 1,220 kilometers in radius, surrounded by a liquid outer core extending to approximately 3,480 kilometers from the center. The liquid outer core is in continuous motion, driven by heat flowing outward from the inner core and the rotation of the Earth. This motion of electrically conducting liquid iron generates electric currents, which in turn produce the magnetic field that surrounds the Earth. This process, called the geodynamo, has been operating for at least 3.5 billion years, as recorded in the magnetization of ancient rocks. Earth's magnetic field deflects the solar wind around the planet and helps protect the surface from cosmic rays and charged particles that would otherwise be harmful to life. Without the magnetic field, the solar wind would gradually strip away the atmosphere, as appears to have happened to Mars. The Earth is approximately 4.54 billion years old. This age has been determined primarily through radiometric dating of the oldest rocks on Earth and of meteorites, particularly a class called carbonaceous chondrites, which are primitive, unprocessed remnants of the solar system's original material and have not been significantly altered by heat or chemical processes since they formed. The decay of radioactive isotopes such as uranium-238 to lead-206 and uranium-235 to lead-207, which occur at known and constant rates, allows the age of a rock to be determined by measuring the ratio of parent-to-daughter isotopes. The oldest minerals found on Earth are zircon crystals from the Jack Hills of Western Australia, which have been dated to approximately 4.4 billion years old. The Earth itself is thought to have formed about 4.54 billion years ago, accreting from the disk of gas and dust surrounding the young Sun. The Moon likely formed from debris ejected when a Mars-sized body collided with the early Earth. The giant impact hypothesis, the currently favoured model for the Moon's origin, proposes that approximately 4.5 billion years ago, a body roughly the size of Mars, sometimes called Theia, struck the young Earth in a grazing collision. The impact melted much of both bodies. Material was ejected into orbit around the Earth, where it coalesced over thousands of years to form the Moon. Evidence supporting this hypothesis includes the Moon's relatively low iron content compared to the Earth. Iron from both bodies would have sunk to the centres of the resulting molten masses, leaving the ejected disk material depleted in iron, and the nearly identical oxygen isotope ratios of Earth and lunar rocks, suggesting they formed from the same reservoir of material. The hypothesis also explains the large angular momentum of the Earth-Moon system, and the Moon's anomalously large size relative to the Earth compared to the moons of other planets. Life on Earth has existed for at least 3.5 billion years. The oldest generally accepted evidence for life consists of fossilized stromatolites, layered structures built by communities of microorganisms, found in rocks in Western Australia approximately 3.48 billion years old. More controversial evidence, including the carbon isotope ratios of carbon inclusions in ancient zircon crystals, suggests life may have existed as early as 4.1 billion years ago, just a few hundred million years after the Earth formed and during a period called the Late Heavy Bombardment, when the inner solar system was being intensively struck by asteroids and comets. The rapid appearance of life after the Earth became habitable has led some scientists to suggest that life arises readily wherever conditions are suitable, though this conclusion remains controversial given that we have only one example of abiogenesis, life arising from non-living chemistry, to study. The Sun is currently about halfway through its main sequence lifetime, Having been burning hydrogen in its core for approximately 4.6 billion years, the Sun has approximately 5 billion years of main sequence life remaining. Over this time, the Sun will gradually become brighter as the helium ash accumulates in its core and the hydrogen-burning shell moves outward. In approximately 1 billion years, the Sun will be about 10% brighter than it is today, bright enough that Earth's surface temperatures will rise beyond the range comfortable for complex life, and the oceans will eventually begin to evaporate. In approximately 3.5 billion years, the Sun may be bright enough to trigger a runaway greenhouse effect on Earth, similar to what occurred on Venus, rendering the planet uninhabitable, regardless of any human intervention. The habitable zone around the Sun, the range of distances at which a planet could maintain liquid water on its surface, will shift outward as the Sun brightens. The most distant object ever observed is a galaxy seen as it was just 300 million years after the Big Bang. The James Webb Space Telescope has pushed the frontier of cosmic observation to within a few hundred million years of the Big Bang. In 2022 and 2023, Webb detected galaxies at redshifts greater than 12, corresponding to a time when the universe was less than 400 million years old. One candidate galaxy, designated JADES-GS-Z13-0, was observed at a redshift of approximately 13.2, placing it at a time just 320 million years after the Big Bang. The light from this galaxy has been travelling for approximately 13.4 billion years to reach Webb's detectors. The galaxies in the early universe observed by Webb are surprising in several ways. Some are more massive and more structured than models predicted for such an early epoch, suggesting that galaxy formation and the growth of supermassive black holes may have proceeded more rapidly in the early universe than previously understood. The universe will eventually reach a state of maximum entropy called the heat death. In the far future, a timescale of trillions upon trillions of years, the universe will exhaust its available free energy. Stars will have burned out. Black holes will have evaporated through Hawking radiation. The last black holes, the most massive ones, will take approximately 10 to the power of 100 years to evaporate completely, a timescale incomprehensibly longer than the current age of the universe. After the last black hole is gone, the universe will consist of a sparse collection of photons, neutrinos, electrons and positrons in a state of maximum entropy. A cold, dark, featureless expanse in which no further work can be done, no structures can form, and nothing of interest can happen. This is the heat death of the universe, the thermodynamic endpoint of cosmic evolution. Whether the universe truly ends in this way depends on the nature of dark energy, and whether the laws of physics as we understand them hold over these extraordinary timescales. There may be other universes beyond our own. The concept of a multiverse, the idea that our universe is not the only one but is one of many, arises naturally in several different theoretical frameworks. In eternal inflation, the rapid expansion of the early universe produces an infinite number of bubble universes, each with its own physical constants and laws. In string theory, the landscape of possible vacuum states of the theory, estimated to number somewhere around 10 to the power of 500, may each be realized in a different region of a vast multiverse. In the many worlds interpretation of quantum mechanics, every quantum measurement causes the universe to branch into multiple copies, each realizing a different outcome. These various multiverse proposals are not all the same idea, they arise from different theories and have different properties, but they share the common feature that our observable universe may be a small part of a much larger reality. Whether any of these proposals constitutes a genuine scientific theory, testable in principle by observation, is a matter of ongoing debate. The night sky is dark because the universe had a beginning. This observation, that the sky is dark at night, seems trivially obvious, but it conceals a profound cosmological puzzle known as Olbers' paradox. If the universe were infinite in age and infinite in extent, with stars distributed uniformly throughout, then every line of sight in any direction would eventually terminate on the surface of a star. The sky should be as bright as the surface of the sun in every direction. The fact that the night sky is dark tells us something fundamental. The universe is not infinitely old. Light from the most distant stars and galaxies has not had time to reach us. The universe had a beginning, and beyond the cosmic horizon, the distance light could have travelled since the Big Bang. There is simply no light to receive. The darkness of the night sky is a consequence of the finite age of the universe, and one of the oldest observational confirmations of the Big Bang model. We are, in the most literal sense, made of stardust. Every atom in your body heavier than hydrogen and most of the helium was forged inside a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron-carrying oxygen through your blood, all of it was synthesized in the nuclear furnaces of stars that lived and died before the solar system formed. The hydrogen in your body is even older than that. Most of it was produced in the first few minutes after the Big Bang, before any stars existed, in a process called Big Bang nucleosynthesis. When you hold your hand in front of your face in the darkness, you're looking at something ancient and strange. Atoms that have been part of interstellar gas clouds, of pre-solar nebulae, of stellar cores burning at millions of degrees. The atoms in your body have existed for billions of years before you were born, and will exist for billions of years after you're gone. You're a temporary arrangement of matter that the universe has been preparing for a very long time. The silence of the cosmos may be the most important unanswered question in science. The Fermi paradox, named after the physicist Enrico Fermi, who is said to have asked at lunch one day, given the vast number of stars in the age of the galaxy, "Where is everybody?" captures a profound puzzle. The Milky Way contains hundreds of billions of stars, many of them billions of years older than the Sun, many of them likely hosting planets, and potentially many of those planets hosting life. Given enough time, even a civilization travelling at a fraction of the speed of light could colonize the entire galaxy in a few tens of millions of years, a short time compared to the age of the galaxy. So where are they? Why is the night sky silent? Why have we detected no unambiguous signals of extraterrestrial intelligence in more than 60 years of searching? The possible answers range from the mundane, intelligent life is rare, or civilizations are short-lived, or communication across interstellar distances is simply impractical, to the deeply unsettling. Perhaps intelligent life always destroys itself before achieving interstellar capability. Perhaps we're alone, or nearly so, in the observable universe. Perhaps the universe is teeming with life, but we're not yet sophisticated enough to notice. Perhaps we are the first. The silence continues, patient and absolute, while we listen. The silence continues, patient and absolute, while we listen. And we have been listening for a long time now. Since 1960, when the radio astronomer Frank Drake pointed a telescope at two nearby sun-like stars and listened for signals, the project he called Ozma, after the queen of a fictional far-off land, humanity has been conducting an intermittent, imperfect, and so far fruitless search for signs of intelligence beyond Earth. The tools have grown vastly more sensitive in the intervening decades. Modern radio telescopes can detect signals far weaker than Drake's equipment could. Automated systems scan millions of radio frequencies simultaneously, and the silence has remained. This does not mean the universe is empty. It means only that we have not yet heard anything. The search has been limited by our technology, our time, and our assumptions about what an extraterrestrial signal might look like. We have examined only a tiny fraction of the stars in the galaxy, monitored only a narrow range of frequencies, listened only for the kind of signal a civilization similar to our own might transmit. The universe is incomprehensibly large, and the search has barely begun. What would change if we found something, a signal, a structure, a biosignature in the atmosphere of a distant planet, is difficult to overstate. It would be among the most significant discoveries in the history of science. It would mean that the emergence of life and intelligence is not unique to Earth. It would mean that the cosmos, in some meaningful sense, is alive. The search for biosignatures in exoplanet atmospheres is one of the most active frontiers in astronomy. A biosignature is a chemical or physical indicator that life is present on a world. The most compelling biosignatures are molecules that, on Earth, are produced almost exclusively by biological processes and would quickly disappear through chemical reactions if not continuously replenished. Oxygen is the most famous example. Earth's atmosphere is approximately 21% oxygen, a highly reactive gas that combines readily with iron, sulfur, and other elements. In the absence of photosynthesis continuously producing it from carbon dioxide, Earth's atmospheric oxygen would be consumed by geological processes in a geologically short time. The persistence of oxygen in Earth's atmosphere is therefore a product of life, and detecting oxygen in the atmosphere of an exoplanet would be a strong hint that something biological might be happening there. Other candidate biosignatures include methane in the presence of oxygen, a combination that reacts rapidly and cannot persist in equilibrium without a continuous source, as well as nitrous oxide and a compound called dimethyl sulfide, produced on Earth by marine algae. The James Webb Space Telescope is now capable of detecting some of these molecules in the atmospheres of exoplanets orbiting nearby stars, making the detection of a potential biosignature a genuine near-term scientific possibility. The habitable zone around a star is not the only place where life might exist. The habitable zone, the range of orbital distances at which liquid water could exist on a planet's surface, is defined with reference to sunlight as the energy source and water as the solvent. But life on Earth has demonstrated that neither of these requirements is absolute. At hydrothermal vents on the ocean floor, entire ecosystems of bacteria, worms, crabs and fish thrive in complete darkness, deriving energy from the chemical reactions between hot mineral-rich water and the cold ocean. These ecosystems demonstrate that life can exist without sunlight. In the solar system, the moons Europa and Enceladus have subsurface oceans kept liquid by tidal heating rather than sunlight. If life can exist in these oceans, and there is no physical reason it could not, then the habitable zone around a star is not the relevant boundary. The relevant question becomes, where in the solar system does liquid water exist? And the answer, it turns out, is that liquid water may be present in a surprisingly large number of places, from icy moons in the outer solar system to the deep subsurface of rocky planets. The most extreme environments on Earth are inhabited. Organisms called extremophiles, life forms that thrive in conditions that would be lethal to most other organisms, have been found in environments that were once considered completely uninhabitable. Thermophiles and hyperthermophiles live in hot springs and hydrothermal vents at temperatures above 80 degrees Celsius, and some archaea can survive in water near or above the boiling point. Psychrophiles live in Antarctic ice and cold, deep-sea environments at temperatures near or below freezing. Acidophiles thrive in highly acidic conditions, including acid mine drainage with a pH near zero. Halophiles live in hypersaline environments, including the Dead Sea and salt flats where the salt concentration is several times that of ordinary seawater. Radio-resistant organisms, most famously Deinococcus radiodurans, can survive doses of radiation thousands of times greater than would kill a human. And tardigrades, microscopic animals sometimes called water bears, can survive the vacuum of space, extreme radiation, desiccation, and temperatures ranging from near absolute zero to above 150 degrees Celsius. The discovery of life in these extreme environments has substantially expanded our conception of where in the solar system and beyond life might be possible. The first exoplanet confirmed around a Sun-like star was discovered in 1995. The planet, designated 51 Pegasi b, orbits a star in the constellation Pegasus approximately 50 light-years from Earth. It was discovered by the Swiss astronomers Michel Mayor and Didier Queloz using the radial velocity method, which detects the slight wobble that an orbiting planet induces in its host star. As the planet orbits, its gravity causes the star to move very slightly toward and away from Earth in a periodic pattern, producing a Doppler shift in the star's spectrum that can be measured with a sufficiently sensitive spectrograph. 51 Pegasi b turned out to be a hot Jupiter, a gas giant planet with roughly half the mass of Jupiter, but orbiting its star in only 4.23 days, at a distance roughly 20 times closer than Mercury orbits the Sun. Its surface temperature is approximately 1000 degrees Celsius. The discovery was initially met with skepticism. No one had expected to find a gas giant so close to its host star, because the standard models of planetary formation predicted that gas giants should form in the cold outer regions of protoplanetary disks. Mayor and Queloz received the Nobel Prize in Physics in 2019 for this discovery. Some exoplanets orbit in the habitable zones of their host stars and may have conditions suitable for liquid water. Among the thousands of confirmed exoplanets, a growing number have been found in the habitable zones of their host stars, with radii suggesting they may be rocky rather than gaseous. The TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets orbiting a red dwarf star approximately 39 light-years from Earth, 3 of which are within the habitable zone. The system has become one of the most intensively studied targets in exoplanet science. Red dwarf stars, which are smaller, cooler, and far longer lived than the Sun, make up approximately 70% of all stars in the galaxy, and because their habitable zones are closer in, habitable zone planets around them complete one orbit in just a few days, making them relatively easy to detect. The TRAPPIST-1 planets are close enough and orbit a star dim enough that the James Webb Space Telescope can search for atmospheres and potentially biosignatures. Early results from Webb have placed limits on the atmospheres of some of the TRAPPIST-1 planets, but the search continues. The solar wind is a continuous stream of charged particles flowing from the Sun in all directions. The solar wind consists primarily of electrons and protons escaping from the Sun's corona at velocities between 300 and 800 kilometers per second. It fills the entire heliosphere, the vast bubble of space dominated by the Sun's magnetic field and particle output, and interacts with every planet and moon in the solar system. At Earth, the solar wind is deflected by the planet's magnetic field, compressing the field on the day side and stretching it into a long tail on the night side, forming the magnetosphere. Where the solar wind meets the magnetosphere, charged particles can be funneled down magnetic field lines toward the poles, producing auroras. At Mars, which lacks a global magnetic field, the solar wind interacts directly with the upper atmosphere, eroding it over geological time. At the outermost reaches of the heliosphere, the solar wind slows and eventually stops where it meets the interstellar medium, a boundary called the heliopause, which Voyager 1 crossed in 2012. The interstellar medium, the space between stars, is not empty. It contains gas at densities of roughly 1 atom per cubic centimetre in the warm neutral medium, falling to far lower densities in the hot ionized medium, and rising to much higher densities in cold molecular clouds. It also contains dust, microscopic grains of silicates, carbon compounds and ice that obscures light from distant stars, dims and reddens their light, and provides surfaces on which chemical reactions can occur in the cold vacuum of interstellar space. Complex organic molecules, including amino acids and their precursors, have been detected in molecular clouds and in interstellar space. The interstellar medium is not a passive backdrop between stars, but an active medium that shapes the formation of new stars and planetary systems, exchanges material with those systems, and serves as the reservoir from which the next generation of stars will form. Radio waves from space were first detected accidentally in 1932. The engineer Karl Jansky, working for Bell Telephone Laboratories, was investigating sources of radio frequency interference affecting transatlantic telephone communications. He built a rotating antenna system and systematically catalogued the sources of interference he detected. Most of the sources turned out to be thunderstorms, either nearby or distant. But one source was different. It was a steady hiss that appeared to rotate with the sky, and repeated on a period of approximately 23 hours and 56 minutes. Jansky correctly identified this as the period of the Earth's rotation relative to the stars, the sidereal day, and concluded that the signal was coming from an astronomical source. He traced it to the centre of the Milky Way. This was the first detection of astronomical radio emission, and it marked the birth of radio astronomy, a field that would go on to reveal the universe in a completely new light, revealing phenomena invisible to optical telescopes, including pulsars, quasars, the cosmic microwave background, and the structure of the interstellar medium. The cosmic microwave background radiation fills all of space uniformly in every direction. It is the oldest light in the universe. Electromagnetic radiation released approximately 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before this moment, called recombination, the universe was opaque. Photons could not travel freely because they were constantly scattering off the dense sea of free electrons. When neutral atoms formed, the photons were suddenly free to travel, and they have been travelling ever since, filling all of space. By now, the universe has expanded by a factor of roughly 1,100 since recombination, and this expansion has stretched the wavelengths of the photons by the same factor, cooling them from the thousands of degrees they had at the moment of release to the current temperature of approximately 2.725 Kelvin, just a few degrees above absolute zero. The cosmic microwave background is visible in every direction of the sky with equal intensity, with tiny temperature fluctuations of roughly 1 part in 100,000 that carry encoded information about the composition, geometry, and early history of the universe. The universe is geometrically flat, to the precision of current measurements. One of the most striking properties of the observable universe, revealed by detailed measurements of the cosmic microwave background, is that its large-scale geometry is flat, Euclidean, In a flat universe, parallel lines remain parallel. The sum of the angles of a triangle is exactly 180 degrees, and the geometry of space on the largest scales is the familiar geometry of ordinary three-dimensional space. This is in contrast to positively curved geometries, like the surface of a sphere, where parallel lines eventually converge and the sum of triangle angles exceeds 180 degrees, and negatively curved geometries, like a saddle, where parallel lines diverge. The flatness of the universe is one of the predictions of inflation. The rapid expansion of the early universe stretched out any initial curvature, just as inflating a balloon makes its surface appear flatter. Measurements from the Planck satellite constrain the curvature of the universe to within a fraction of a percent of flat, consistent with inflation's prediction. The first stars in the universe formed approximately 100 to 200 million years after the Big Bang. Before the first stars ignited, the universe was dark, filled with hydrogen and helium gas, cooling and beginning to clump under the influence of gravity but producing no light of its own. This period is called the Cosmic Dark Ages. Gradually, over tens to hundreds of millions of years, small pockets of gas collapsed under their own gravity, heating as they compressed until nuclear fusion ignited at their centers. The first stars, called Population 3 stars by astronomers, were unlike any stars that exist today. They formed from gas that contained only hydrogen and helium, with no heavier elements because no previous stars had yet existed to produce them. Without the cooling effects of carbon, oxygen, and other heavy elements, the gas clouds that formed the first stars could not cool as efficiently, and the first stars are thought to have been extremely massive, perhaps hundreds of times the mass of the Sun, burning intensely hot and blue-white, consuming their fuel rapidly, and living for only a few million years before dying in powerful supernova explosions. These explosions scattered the first heavy elements, carbon, oxygen, nitrogen, iron, into the interstellar medium, seeding the next generation of star formation with the building blocks of rocky planets, and eventually life. Quasars are among the brightest objects in the observable universe. A quasar, the word is a contraction of quasi-stellar radio source, is an extremely luminous active galactic nucleus, powered by a supermassive black hole, accreting material at an enormous rate. As gas and dust fall toward the black hole and spiral inward through an accretion disk, they heat to temperatures of millions of degrees and radiate enormous amounts of energy across the entire electromagnetic spectrum, from radio waves to gamma rays. The most luminous quasars outshine their entire host galaxies by factors of hundreds or thousands, releasing in a second as much energy as the Sun emits in a million years. Quasars are seen predominantly at large distances and therefore at early cosmic times. They were most abundant when the universe was between 2 and 3 billion years old, corresponding to a redshift of approximately 2, when galaxy mergers and interactions were more frequent and supermassive black holes had abundant material to consume. The quasar nearest to Earth, 3C273, is approximately 2.4 billion light-years away, and is still bright enough to be visible through a small amateur telescope. Some galaxies are actively cannibalizing smaller neighbors. Galaxy cannibalism, the process by which a large galaxy absorbs smaller satellite galaxies, is a normal part of how large galaxies grow. The Milky Way itself is currently in the process of absorbing several smaller galaxies, most notably the Sagittarius dwarf spheroidal galaxy, which has been orbiting the Milky Way for billions of years and is in the process of being torn apart by tidal forces. Streams of stars pulled from the Sagittarius dwarf now form a vast arc encircling the Milky Way, detectable through their distinctive chemical compositions. The large and small Magellanic Clouds, the two irregular satellite galaxies visible to the naked eye from the southern hemisphere, are also being gravitationally influenced by the Milky Way and will eventually be fully absorbed into it. The Magellanic Stream, a long arc of neutral hydrogen gas stretching across a significant fraction of the southern sky, has been drawn out of the Magellanic Clouds by the Milky Way's gravity. The largest known stars would engulf the entire inner solar system if placed at the centre of our own. UY Scuti, mentioned earlier, is one of the largest known stars by radius, but there are others of comparable or greater size. Stephenson 2-18, a red hypergiant in the constellation Scutum, may have a radius approximately 2,150 times that of the Sun. If placed at the Sun's position, its surface would extend well beyond the orbit of Saturn. Stars of this size are nearing the limit of what a star can be without becoming unstable. They pulsate, losing mass at enormous rates through stellar winds, and are typically near the end of their lives. The largest stars do not necessarily have the greatest masses. Mass and radius do not scale together in the way intuition might suggest. The most massive stars, which can exceed 100 solar masses, are often compact blue hypergiants, rather than the diffuse red supergiants that hold the size records. The universe contains more stars than grains of sand on all of Earth's beaches. The estimated number of stars in the observable universe, taking into account the upward revision to approximately 2 trillion galaxies, each containing on average a few hundred billion stars, is approximately 10 to the power of 24, a 1 followed by 24 zeros. The number of grains of sand on all of Earth's beaches and deserts combined is estimated to be roughly 7.5 times 10 to the power of 18, a 7.5 followed by 18 zeros. The number of stars exceeds the number of grains of sand by a factor of roughly 100,000, and yet despite this staggering number of stars, each one a sun, many of them with their own planetary systems, the vast majority of the observable universe, by volume, is empty space. The average density of matter in the observable universe is approximately 6 protons per cubic meter. The universe is almost entirely nothing, with islands of something separated by immense voids. The age of the universe can be read in the light of distant galaxies. When astronomers observe a galaxy 10 billion light-years away, they are seeing it as it was 10 billion years ago. The light that reaches our telescopes tonight left that galaxy when the universe was less than 4 billion years old, before the solar system existed, before the Earth formed. This is why deep-field images, long-exposure photographs taken by the Hubble Space Telescope, and now the James Webb Space Telescope, pointing at small blank patches of sky for days or weeks at a time, are simultaneously photographs of distant space and photographs of the distant past. The Hubble Ultra Deep Field image taken in 2003 and 2004 revealed approximately 10,000 galaxies in a patch of sky roughly 1/13 the diameter of the full moon, most of them billions of light-years away, most of them seen as they appeared billions of years before the solar system formed. To look at a deep field image is to see not one moment in time but a cross-section of cosmic history. Gravitational lensing allows astronomers to see objects that would otherwise be too faint or too distant. When light from a distant source passes near a massive object, a galaxy cluster for example, the mass curves the space-time around it, bending the path of the light. This effect, predicted by general relativity and first observed during the solar eclipse of 1919, acts as a natural telescope. A massive galaxy cluster between Earth and a distant galaxy can magnify the galaxy's light by factors of 10, 100, or even more, allowing astronomers to study objects that would otherwise be too faint to observe. Gravitational lensing also produces distinctive visual effects. Images of the background source can be stretched into arcs, split into multiple images, or, in the rare case where the source, the lensing mass, and the observer are perfectly aligned, arranged into a ring of light called an Einstein ring. The most distant objects observed by the James Webb Space Telescope have often been discovered or studied with the aid of gravitational lensing by foreground galaxy clusters. The mass of a galaxy can be measured by the motions of stars and gas within it. The speed at which stars orbit the center of a galaxy depends on the mass enclosed within their orbit, the same principle that governs the orbital velocities of planets around a star. By measuring the rotational velocities of stars and gas at different distances from the galactic center, astronomers can construct a rotation curve, a plot of orbital velocity versus distance from the center, and use it to infer the distribution of mass. When astronomers first constructed rotation curves for spiral galaxies in the 1970s, primarily through the work of Vera Rubin and Kent Ford, they found something unexpected. Instead of decreasing with distance from the center as the visible matter would predict, the rotation curves remained roughly flat far into the outskirts of the galaxies, where little visible matter was present. The only way to explain this was to postulate that the galaxies were embedded in vast halos of invisible matter, what we now call dark matter. The flat rotation curves of spiral galaxies remain one of the strongest pieces of evidence for dark matter, and were among the earliest indications that most of the universe's mass is not visible. The first images of a black hole's shadow were produced by combining data from 8 radio telescopes on different continents. The Event Horizon Telescope is not a physical instrument, but a virtual telescope. a collaboration that synchronizes radio telescopes spread across the globe from Hawaii to the South Pole to observe the same source simultaneously. By comparing the signals received at different telescopes and accounting for the precise timing using atomic clocks, the collaboration can synthesize a telescope with an effective aperture equal to the diameter of the Earth, achieving angular resolution sufficient to resolve the event horizon shadows of the two black holes targeted, M87 star and Sagittarius A star. The technique, called very long baseline interferometry, requires recording enormous amounts of data, petabytes from each observation run, which are then shipped physically on hard drives to central processing facilities and combined. The resulting images, released in 2019 and 2022 respectively, represented the culmination of years of technical development and international scientific collaboration, and confirmed general relativity's predictions about the appearance of a black hole in striking detail. Interstellar objects have passed through the solar system. In 2017, astronomers detected an object passing through the solar system that had clearly originated from outside it, the first interstellar object ever confirmed. Designated 1I/2017 U1 and nicknamed Oumuamua, meaning scout or messenger in Hawaiian, the object was discovered after it had already passed its closest approach to the Sun and was recelerating outward. Its trajectory was hyperbolic. It was moving too fast to be gravitationally bound to the Sun, and its excess velocity was consistent with it having originated in the interstellar medium. Oumuamua was puzzling in several respects. It appeared to be highly elongated or pancake-shaped based on its light curve. It showed an anomalous acceleration away from the Sun that could not be explained by gravity or the pressure of solar radiation if it were a rocky body, and no cometary activity, no gas or dust, was detected. Its origin and nature remain uncertain. In 2019, a second interstellar object, designated 2I/Borisov, was discovered while still approaching the inner solar system. Borisov behaved more like a typical comet, with detectable outgassing, and showed no anomalous acceleration. The detection of two interstellar objects within just 2 years suggested that interstellar visitors to the solar system are more common than previously appreciated. The surfaces of many solar system bodies are cratered by billions of years of impacts. The Moon, Mercury, Mars, and many moons and asteroids bear the record of the solar system's violent early history, preserved on their surfaces as overlapping craters ranging in size from microscopic pits to vast basins hundreds of kilometers across. Earth was similarly bombarded in its early history, but geological processes, plate tectonics, erosion, volcanism, and the work of water have erased most of the ancient impact record. Only a few hundred impact craters are clearly identifiable on Earth's surface today, compared to the millions visible on the Moon. The largest confirmed impact crater on Earth is the Vredefort Dome in South Africa, approximately 300 kilometers across and approximately 2 billion years old. The period of intense bombardment that dominated the first several hundred million years of the solar system's history, called the Late Heavy Bombardment, may have been triggered by a rearrangement of the orbits of the giant planets, which scattered large numbers of asteroids and comets into the inner solar system. The asteroid that struck the Earth 66 million years ago released energy equivalent to billions of nuclear bombs. The Chicxulub impactor, named after the Chicxulub crater it produced, centered near the town of Chicxulub Puerto on the Yucatan Peninsula of Mexico, was approximately 10 to 15 kilometers in diameter and struck the Earth at an estimated speed of roughly 20 kilometers per second. The impact released an estimated energy of approximately 100 teratons of TNT, roughly 1 billion times more energetic than the atomic bomb dropped on Hiroshima. The immediate effects included an enormous explosion, a global firestorm ignited by ejecta raining back down through the atmosphere, massive tsunamis, and a cloud of dust and sulfur aerosols that blocked sunlight for months or years. The resulting darkness and cooling, sometimes called an impact winter, caused the collapse of photosynthesis and the food webs that depended on it. Approximately 75% of all species on Earth went extinct, including all non-avian dinosaurs. The impact opened ecological space that was subsequently filled by the adaptive radiation of mammals, eventually leading tens of millions of years later to a small, large-brained primate species that would build radio telescopes and wonder whether anyone else was out there. The Hubble Space Telescope has been operating for more than 3 decades. Launched on April 24, 1990, the Hubble Space Telescope has become one of the most productive scientific instruments in history. It orbits the Earth at an altitude of approximately 540 kilometers above the distorting effects of the atmosphere and has a primary mirror 2.4 meters in diameter. After a flaw in the mirror was discovered, the mirror had been ground to the wrong shape with extraordinary precision. A servicing mission in 1993 corrected the optics and transformed Hubble from an embarrassment into an icon. 5 subsequent servicing missions by space shuttle crews upgraded Hubble's instruments and extended its operational life. Hubble has contributed to an enormous range of discoveries, from the confirmation of the accelerating expansion of the universe to the measurement of the Hubble constant. From the first detailed images of galaxy formation in the early universe to the atmosphere of exoplanets. It has taken more than 1.5 million observations and produced more than 19,000 peer-reviewed scientific papers. Light carries momentum, and the pressure of sunlight can push objects through space. This effect, radiation pressure, is small but real, and it has measurable consequences for small objects in the solar system. The acceleration of comets and asteroids by radiation pressure, called the Yarkovsky effect, can shift the orbits of small bodies over millennia. For spacecraft, radiation pressure must be accounted for in precision navigation. The anomalous acceleration of the Pioneer 10 and Pioneer 11 spacecraft, which puzzled scientists for decades, was eventually explained primarily by the anisotropic emission of thermal radiation from the spacecraft's own warm electronics, a subtle but real force. Proposed solar sails, spacecraft that use large reflective surfaces to harness the pressure of sunlight for propulsion, would exploit this effect deliberately, potentially allowing travel through the solar system without fuel. The Japanese space agency JAXA deployed the first successful solar sail, Icaros, in 2010, demonstrating the feasibility of the concept. The Drake equation attempts to estimate the number of communicating civilizations in the Milky Way. Formulated by Frank Drake in 1961, the equation expresses the number of technologically communicating civilizations in the galaxy as a product of several factors: the rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those planets that are potentially habitable, the fraction on which life actually arises, the fraction on which intelligent life arises, the fraction that develop technology and attempt communication, and the average lifetime of such a civilization. For most of these factors, we now have reasonable estimates. The rate of star formation, the fraction of stars with planets, and the fraction of potentially habitable planets are all constrained by observation. The remaining factors, the emergence of life, the emergence of intelligence, the development of technology, and the longevity of civilizations remain highly uncertain. Optimists plug in favourable values and conclude that the galaxy should be teeming with communicating civilizations. Pessimists use less favourable estimates and conclude that we may be alone. The equation is less a calculation than a framework for organising our ignorance. The concept of terraforming, transforming a planet to make it suitable for human habitation, has been discussed seriously by scientists. Mars is the most frequently discussed candidate for terraforming, given its relative proximity and the evidence that it once had a thicker atmosphere and liquid water. Proposed approaches include releasing greenhouse gases into the Martian atmosphere to warm it, redirecting comets and asteroids to deliver volatiles, and manufacturing a planetary magnetic field to protect the atmosphere from solar wind erosion. The timescales involved in any realistic terraforming scenario are vast, centuries to millennia at minimum, possibly tens of thousands of years for a full transformation. Whether such a project is technically feasible, ethically justifiable, particularly if Mars harbours any extant life in its subsurface, and worth the effort given alternative approaches to space habitation, is a subject of ongoing discussion among scientists and policymakers. The Sun emits nearly all of its energy as light and heat, but a small fraction escapes as neutrinos. Of the approximately 3.8 times 10 to the power of 26 watts of power the Sun radiates, roughly 2% is in the form of neutrinos, ghostly particles that interact with matter only through the weak nuclear force and gravity. This means they pass through the Sun itself virtually without interaction and escape directly from the core at the moment they are produced, carrying fresh information about what is happening inside the Sun right now. By contrast, Photons produced in the solar core take tens of thousands of years to diffuse outward to the surface, bouncing between particles in a random walk. The neutrinos you could in principle detect right now, if you had the right instrument, left the Sun's core only 8 minutes ago at the same time as the light you can see. Approximately 65 billion solar neutrinos pass through every square centimetre of the Earth's surface every second, most of them arriving from directly ahead during the day and having passed through the entire Earth at night, virtually unaffected. Some of the largest structures in the solar system are invisible. The Roche limit is the distance from a massive body within which a smaller body held together only by its own gravity will be torn apart by tidal forces. Within the Roche limit of a planet, moons cannot form by accretion. Instead, any material present tends to be spread into rings. Saturn's rings lie within Saturn's Roche limit for ice, the primary material of the rings. Similarly, the rings of Uranus and Neptune lie within those planets' Roche limits. Beyond the Roche limit, moons can form and persist. The boundary is invisible, but determines the structure of planetary systems on the scale of hundreds of thousands of kilometers. Similarly invisible is the magnetosphere, the region of space dominated by a planet's magnetic field, which for Earth extends approximately 60,000 kilometers toward the Sun and stretches into a long tail on the night side that extends millions of kilometers in the antisolar direction. The surface of the Sun rotates differentially. The equator rotates faster than the poles. The Sun is a ball of plasma rather than a solid body, and different latitudes rotate at different rates. The solar equator completes one rotation in approximately 25 days, while regions near the poles take approximately 35 days. This differential rotation winds up and distorts the Sun's magnetic field, which threads through the solar interior and surface. Over time, the magnetic field lines become increasingly tangled and stressed, eventually breaking through the surface as sunspots. Dark, relatively cool regions where the magnetic field is particularly strong and inhibits convection. The distortion of the magnetic field by differential rotation drives the approximately 11-year solar cycle, during which the number and activity of sunspots rises and falls. At solar maximum, the Sun's magnetic poles flip. North becomes south and south becomes north, and the cycle then begins again with the reversed polarity. The causes of this cycle and the mechanisms by which the magnetic field is generated and maintained are understood in broad outline but not in full detail. Neptune was discovered through mathematical prediction, before it was observed telescopically. In the mid-19th century, astronomers noticed that Uranus was not following the orbital path predicted by Newtonian gravity, given the known masses and positions of the other planets. The French mathematician Urbain Le Verrier and the English mathematician John Couch Adams independently calculated that a previously unknown eighth planet, positioned at a specific location, could explain the perturbations in Uranus's orbit. Le Verrier communicated his prediction to the Berlin Observatory, and on September 23, 1846, the astronomer Johann Galle pointed a telescope to the predicted location and found Neptune within 1 degree of where Le Verrier had predicted it would be. The discovery of Neptune, one of the great triumphs of 19th century science, demonstrated that Newton's law of gravity could be used to discover new worlds from the comfort of an office, without any telescope at all. Uranus rotates on its side with an axial tilt of approximately 98 degrees. All the planets in the solar system rotate on axes that are tilted to various degrees relative to their orbital plane. Earth's axial tilt of approximately 23.5 degrees is responsible for the seasons, but Uranus's axial tilt of approximately 98 degrees means it rotates nearly on its side. Its north pole alternately points toward the Sun and away from it as it completes one orbit every 84 years. During the decades when a pole is pointing toward the Sun, the polar region receives 42 years of continuous sunlight, while the rest of the planet is in darkness. The cause of Uranus's extreme axial tilt is not entirely certain, but the most widely accepted hypothesis is that early in the solar system's history, Uranus was struck by a large body, perhaps 1 to 3 times the mass of the Earth, that knocked it onto its side. The coldest natural temperature ever measured in the solar system was recorded on the Moon. Despite the Moon's proximity to the Sun, measurements by NASA's Lunar Reconnaissance Orbiter have recorded temperatures as low as approximately -238 degrees Celsius in permanently shadowed craters near the lunar poles, colder than the average surface temperature of Pluto, and among the coldest naturally occurring temperatures measured anywhere in the solar system. These extraordinarily cold temperatures occur because the permanently shadowed craters have not received direct sunlight in billions of years, and the Moon's lack of atmosphere means there is no heat transport by conduction or convection from warmer regions. The Moon effectively acts as a natural cryogenic laboratory in these locations, preserving volatiles, including water ice, that have been deposited there over billions of years. The James Webb Space Telescope can observe wavelengths of light invisible to human eyes. Webb observes primarily in the infrared, wavelengths longer than visible light, rather than the visible wavelengths that Hubble was designed around. This choice is deliberate. As the universe expands, the light from distant galaxies is redshifted. Its wavelengths are stretched by the expansion of space between its source and us. The most distant galaxies, at the highest redshifts, have their original ultraviolet and visible light stretched into the infrared by the time it reaches us. Hubble, limited to ultraviolet and visible wavelengths, could not detect this light. Webb, with its infrared sensitivity, can see through the redshift to the most distant and therefore earliest galaxies. Webb also observes through clouds of dust that scatter visible light but transmit infrared, allowing it to peer into star-forming regions and see the young stars and protoplanetary disks forming within them. Its combination of large mirror, cold operating temperature, which reduces the thermal noise of the instrument itself, and infrared sensitivity makes it by far the most powerful astronomical observatory ever deployed. The universe was opaque for the first 380,000 years of its existence. In the first moments after the Big Bang, matter and energy were so compressed and hot that the universe consisted of a plasma of quarks and gluons. As the universe expanded and cooled, protons and neutrons formed within the first few minutes, followed by the nuclei of helium and trace amounts of lithium through Big Bang nucleosynthesis. But the universe remained far too hot for electrons to bind to nuclei. Any atom that formed was immediately ionized again by the intense radiation filling the space. For 380,000 years, the universe remained an opaque fog of plasma, in which photons scattered continuously off free electrons unable to travel freely. At recombination, when the temperature fell below approximately 3000 Kelvin, electrons and protons combined into neutral hydrogen for the first time, and the fog cleared. The photons released at that moment have been travelling ever since and reach us today as the cosmic microwave background, the oldest light we can ever observe. The very centre of our galaxy is hidden from visible light telescopes by dense clouds of dust. The galactic centre, approximately 26,000 light-years away, is obscured by so many intervening dust clouds that visible light from that region is almost completely absorbed before it reaches us. An observation in visible light in the direction of the galactic centre would show nothing of the centre itself. But infrared and radio wavelengths penetrate the dust, and observations at these wavelengths have revealed the galactic centre in extraordinary detail. The region within a few light-years of Sagittarius A star is densely packed with stars, far more densely than the solar neighbourhood, and the orbits of these stars have been tracked for decades by telescopes including the Keck Observatory in Hawaii and the Very Large Telescope in Chile. The stars move at enormous velocities, some reaching several % of the speed of light at their closest approaches to Sagittarius A star. The detailed study of these stellar orbits, which obey the laws of gravity in the way expected for a 4 million solar mass object at their centre, provided some of the most compelling evidence for the existence of a supermassive black hole at the galactic centre before the Event Horizon Telescope imaged it directly. The astronomers who led these observations, Reinhard Genzel and Andrea Ghez, shared the Nobel Prize in Physics in 2020. Every star visible to the naked eye is in the Milky Way. On a clear dark night, far from city lights, the human eye can detect approximately 5,000 to 10,000 stars. Every single one of them, without exception, is a member of the Milky Way galaxy. The nearest star beyond the Milky Way, in the Andromeda Galaxy, the nearest large galaxy, is approximately 2.5 million light-years away, far too faint to be seen without a telescope. The Andromeda Galaxy itself is visible to the naked eye as a faint smudge of light in the constellation Andromeda on a clear night, but what you are seeing is not individual stars, but the combined light of hundreds of billions of stars, blurred together by distance into a faint glow. The most distant object visible to the naked eye without any optical aid is typically the Andromeda Galaxy, or, under exceptional conditions, the Triangulum Galaxy, approximately 2.7 million light-years away. Everything else you see in the night sky is part of our own galaxy, our own cosmic neighbourhood, which despite its apparent vastness is just one small corner of a universe incomprehensibly larger. A total solar eclipse is a coincidence of extraordinary precision. The Sun is approximately 400 times larger in diameter than the Moon, but it is also approximately 400 times farther away. This remarkable coincidence, which is exactly that, a coincidence not a product of any physical law, means that the Sun and Moon appear almost exactly the same size in Earth's sky. During a total solar eclipse, when the Moon passes directly between the Earth and the Sun, the Moon's disk covers the Sun's disk almost exactly, momentarily blocking the brilliant photosphere and revealing the corona, the Sun's outer atmosphere, as a ghostly halo of white light surrounding the dark circle of the Moon. A slightly larger or closer Moon would cover the corona as well. A slightly smaller or more distant Moon would not cover the Sun completely, and the corona would never be visible. The corona was first studied in detail during total solar eclipses, and many discoveries about the Sun's atmosphere were made by scientists who travelled to the narrow paths of totality, typically only a few hundred kilometres wide, where total eclipses are visible. The universe may have no centre and no edge. Just as the surface of a sphere has no centre point and no edge, every point on the surface is equivalent to every other. The universe may be finite but unbounded. An observer anywhere in such a universe would see themselves as being at the centre of the observable universe, not because they are at a special location, but because they can see only as far as light has had time to travel since the Big Bang. The observable universe has a centre, the observer, but the universe itself may not. Whether the universe is finite or infinite, bounded or unbounded, is a question that current observations cannot definitively answer. The cosmic microwave background suggests that the universe is nearly flat, which is consistent with an infinite universe, but cannot rule out a very large finite one. The answer may be fundamentally unknowable with any technology we can imagine, because regions beyond the cosmic horizon are, by definition, causally disconnected from us. Space is not truly empty, even in the interstellar void. Between the stars, in the most rarefied regions of the interstellar medium, there is on average approximately 1 atom per cubic centimetre, overwhelmingly hydrogen, with some helium and trace amounts of heavier elements. This is an extraordinarily good vacuum by laboratory standards. The best vacuums achievable on Earth contain billions of atoms per cubic centimetre. But even this tenuous gas is not nothing, and at the quantum level, as discussed in the context of the quantum vacuum, even truly empty space seethes with virtual particle pairs appearing and disappearing on timescales too brief to observe directly. The Casimir effect, a measurable force between closely spaced metal plates in vacuum, caused by differences in the quantum vacuum energy between the plates and outside, is a direct demonstration that empty space is not truly empty, but contains energy even in its ground state. The universe, at every scale and in every location, is more interesting than it appears. The night sky, examined carefully, contains the entire history of the cosmos. The light reaching your eyes on any dark night has travelled for many different amounts of time. Some of it left nearby stars only a few years ago. Some left stars at the far edge of the Milky Way tens of thousands of years ago. Some, the light from Andromeda, visible as that faint smear in the constellation Andromeda, left its source 2.5 million years before it reached you. The light from the most distant quasars and galaxies detectable by our telescopes left those objects billions of years ago, when the universe was young and very different from what it is today. The sky is not a flat backdrop with points of light pasted onto it. It is a window through time, a record of everything that has happened since the universe began, displayed simultaneously across the entire celestial sphere. To look up at the sky is to see the universe as it was across all of cosmic history, layered from the nearby and recent to the distant and ancient, all arriving at your eyes in the same moment, as if the universe was showing you everything at once. And here, in a room with dark windows and a still ceiling, the light from those distant places is still arriving. Even now, as the sounds of the day have faded and the hours have grown late and the ordinary concerns of ordinary life have loosened their hold on your attention, photons from distant stars are passing through the walls and through your body without interaction, carrying information from a universe far larger and far stranger than the one you navigate from day to day. The cosmos is not something you look at occasionally through a telescope. It is something you are inside of always. a participant in a process that began 13.8 billion years ago and will continue for trillions of years to come. You're made of atoms forged in stellar cores. Your hydrogen is as old as the universe itself. You're breathing oxygen produced by photosynthesis in organisms that lived and died hundreds of millions of years before the first human being existed. You are warmed by a star that converts 600 million tons of hydrogen to helium every second, 8 minutes away at the speed of a light. You live on a rocky planet that formed from the disk of material surrounding a young star, in an unremarkable arm of an ordinary galaxy, in a small local group of galaxies, in a supercluster, in the cosmic web, in an observable universe containing 2 trillion galaxies, in a universe that may be finite or infinite, alone or populated, one of many or the only one, and we do not yet know which. These are not small questions. They are, in some sense, the only questions. The questions that physics and astronomy have been asking for centuries, and that each generation of scientists has pushed further toward an answer without ever quite reaching it. How large is the universe? How old? What is it made of? Are we alone? What came before? What comes after? Each answer opens new questions. Each discovery reveals new mysteries. The frontier does not retreat as we advance. It expands. And this perhaps is the most remarkable fact of all, that the universe produced, in this particular corner of itself, at this particular moment in its history, creatures capable of asking these questions. Creatures with brains built from atoms powered by chemistry, shaped by billions of years of evolution toward organisms that look up at the night sky and wonder what they are looking at. Creatures that built telescopes and mathematics and spacecraft and radio receivers and then pointed them outward, toward the darkness, with no guarantee of finding anything but the compulsion to look anyway. The silence continues. The questions remain open. The universe keeps its secrets with the same patience it has always kept them. Vast, ancient, indifferent, and astonishing. Rest now. The sky outside holds all of it in place, the same as it always has. The nearby stars and the distant galaxies, the expanding space between them, the cosmic microwave background suffusing everything with its faint warmth, the dark matter halos invisible around every galaxy, the dark energy pushing it all apart at an accelerating rate. None of it requires your attention to continue. The photons are travelling, the stars are burning, the black holes at the centres of distant galaxies are accreting their slow meals. The neutrinos from the sun's core are passing through the Earth, through this building, through you, without pausing. Let your breathing slow. The universe does not need anything from you tonight.